This senior design team was tasked with evaluating improvements for Climax Molybdenum's Henderson Mill drinking water treatment plant. Henderson operations consist of a mine and mill separated by a 14-mile pipeline that sends ore from the mine to the mill for processing. Henderson Mill is located in Grand County, Colorado, at an elevation of approximately 9,200 feet. The mill serves 120 employees with a potable water demand of 24 gallons per minute. The source water for this treatment plant is Ute Creek Reservoir, highlighted by the red circle, and is located just down the road from the mill. There has been historic distrust in the drinking water at Henderson Mill due to taste and temperature issues at the taps and rumors of disinfection byproducts. These rumors have caused the employees to refuse the potable water treated on site and opt for bottled water. Plummer Associates Incorporated was hired in 2009 by the mill to modify the drinking water treatment plant to address these quality concerns, and since then, Plummer has already made the necessary updates. However, for the sake of senior design, this team was provided with 2009 site layouts and water quality data and asked to tackle this issue as if we were consultants hired by the mill originally in 2009 to address these water quality concerns. The first step for the design team was determining the constituents of concern using 2009 data. While iron, manganese, and turbidity in the source water were above regulatory limits, the primary water quality concern was disinfection byproducts in the distribution system, caused by inadequate total organic carbon, or TOC, removal in the treatment system. The next step for this design team was to conduct an extensive literature review to determine treatment processes that could be easily retrofitted to the 2009 system that could also achieve excellent TOC removal. The goal with these designs was to decrease TOC in the water during disinfection to decrease the disinfection byproduct formation potential in the distribution system. Due to site constraints, safety concerns with using chlorine dioxide, maintenance considerations, and the desire to design a novel approach, the team selected treatment option 1 for the final design. This treatment option consists of primary filtration, ozone contact, microfiltration, biologically active filtration columns, and disinfection. The second semester of this project was dedicated to designing the two major components of this system, the ozone injection and the biologically active filtration columns. The major components of the ozone process was the pressure swing absorption system with air purification and pre-treatment on site, as well as the side stream ozone venturi injector. Major components of the biologically active filtration system included the two filter columns, the backwash holding tank, the air compressor and backwash pump, as well as appropriate connections for filtration, backwash, and air scour. The team also performed chlorine contact calculations to ensure the current dose was appropriate for the desired residual of 1 milligram per liter. Final components of the design package presented to the client included a cost estimation of new components, which priced the system just under $115,000. An evaluation of the power requirements was completed for total energy cost assessment and consumption, as well as preventative maintenance measures were outlined for both systems. Hydraulic calculations were completed for the entire system, beginning at the raw water storage tanks and ending at the exit to the biologically active filtration columns. These calculations were then used for pump selection and placement. The final deliverable presented for this project included a complete community engagement plan, including presentation slide sets, speaker notes, and a flyer intended to be distributed at the water taps at the mill to try and establish trust between the employees and the drinking water treatment plant.